Hello everyone. I am Tulsi Prasad, studying in Sri Venkateswara College of India. Today I am going to explain the topic of cyclic groups and cosets. Introduction to cyclic groups. Cyclic groups are fundamental concept in group theory. They are groups that can be generated by a single element. Understanding cyclic groups is essential for studying more complex algebraic structures. Definition of a cyclic group. A cyclic group is defined as a group G that can be expressed as G is equal to G for some element G. The element G is known as a generator of the group. All elements of the group can be obtained by taking powers of G. Notation and terminology. The notation G is equal to small g implies that every element in G can be written as G power n for some integer n. If the group is finite, the order of the group is number of distinct elements generated. The order of the generator G is the smallest positive integer k such that G power k is equal to E, where E is the identity element. Examples of cyclic groups. The set of integers under addition Z is a classic example of an infinite cyclic group. The group of integers modulo n denoted as Zn is a finite cyclic group. Each cyclic group can be represented in terms of its generators, such as 1 for Z and 1 modulo n for Zn. Properties of cyclic groups. Every subgroup of a cyclic group is also cyclic. The order of an element in a cyclic group divides the order of an group itself. A cyclic group of order n has exactly n distinct elements. Subgroups of cyclic groups. Is G is a cyclic group of order n, then the subgroups corresponds to the divisors of n. Each subgroup can be generated by G power n by D, where D is a divisor of n. The number of subgroups of a cyclic group of order n is equal to the number of divisors of n. Finite cyclic groups. A finite cyclic group of order n can be represented as Zn. The group operation is addition modulo n. The elements of Zn are 0, 1, 2, up to n minus 1. Infinite cyclic groups. The group of integers Z is an cyclic example of an infinite cyclic group. The operation is standard addition and it contains infinitely many elements. The generator of Z can be taken as 1 or minus 1. Generators of cyclic groups. A group G is equal to G can have multiple generators. For example, in Z6 both 1 and 5 can serve as generators. In general, if G is a generator of a cyclic group of order n, then G power k is also a generator if k and n are coprime. Cyclic groups and group homomorphisms. A homomorphism is a structure preserving map between two groups. Any homomorphism from a cyclic group is a completely determined by its action on the generator. The image of a generator under a homomorphism will generate the image group. Applications of cyclic groups. Cyclic groups are used in various areas of mathematics, including number theory and cryptography. These serve as building blocks for more complex algebraic structures. Many algorithms in computer science leverage properties of cyclic groups for efficiency. Cyclic groups in cryptography. Cyclic groups play a crucial role in public key cryptography systems such as Diffie-Hellman. They provide a secure way to exchange keys over an insecure channel. The hardness of certain problems in cyclic groups underpins the security of these methods. Lagrange's theorem. Lagrange's theorem states that the order of a subgroup divides the order of the group. This is particularly relevant for cyclic groups, where all subgroups are cyclic. It provides insight into the structure and classification of subgroups. If G is a finite group, H is a subgroup of G, then H divides order of H divides order of G. The number of distinct left cosets of H in G is order of G divides by order of H. Cyclic group representation. Cyclic groups can be represented using Kelly tables or diagrams. Such representation facilitate understanding of the group structure and operations. Visualization here aids in exploring the relationships between elements. Direct products and cyclic groups. The direct product of two cyclic groups is also cyclic if the orders are coprime. This property allows for the construction of larger cyclic groups from smaller ones. It illustrates the interconnectedness of group theory concepts. Finite abelian groups. A very finite abelian group can be expressed as a direct sum of cyclic groups. This classification theorem highlights the significance of cyclic groups in group theory. Understanding the structures is crucial for deeper studies in algebra. The structure of finitely generated abelian groups. Theorem Fundamental theorem of finitely generated abelian groups. Every finitely generated abelian group G is isomorphic to a direct product of cyclic groups in the form where the p are coprimes not necessarily distinct and the r are positive integers. Summary of key concepts. Cyclic groups are generated by a single element and have many important properties. They play a vital role in both theoretical and applied mathematics. Recognizing the significance of cyclic groups and enhance understanding of algebraic structures. Introduction to cosets. Cosets are fundamental concepts in group theory. They arise from the interaction of a subgroup with a group. Understanding cosets is a vital for exploring quotient groups and Lagrange's theorems. Basic definitions. A group is a set equipped with an operation satisfying certain properties. A subgroup is a subset of group that is itself a group under the same operation. Cosets are formed when you multiply all elements of a subgroup by fixed group. Types of cosets. There are two types of cosets, left cosets and right cosets. A left coset is formed by multiplying a subgroup of an element by group element. A right coset is formed by multiplying a subgroup of right by the group element. Left cosets. The left coset of a subgroup order of H in a group divides the order of G with an element order of G is denoted by J of H. It consists all the elements of the form GH where order of H is in order of H. Left cosets partition the group into disjoint subsets. Right cosets. The right coset of a subgroup H in a group G with an element small g is denoted order of G Hg. It consists of all elements of the form small hg where h is in divides h. Like left cosets, right cosets also partition the group into disjoint subsets. Notation. Left cosets are written as gh while right cosets are written as hg. The notation helps distinguish between two types of cosets. Understanding the notation is crucial for effectively communicating in group theory. Properties of cosets. All cosets of subgroup have same number of elements as the subgroup itself. Cosets are either distinct or identical. They do not overlap. The collection of all left cosets all right cosets of subgroup forms a partition of group. Coset representatives. A coset representative is a member of coset. Each coset can be uniquely identified by one of its representatives. Choosing a representative helps in analyzing the structure of groups. Index of a subgroup. The index of a subgroup H in a group divides the G is the number of distinct cosets of H in G. It is denoted by G is to H, order of G is to H. The index provides insights into the size relationship between groups and their subgroups. Examples of cosets. Consider the group math Z Z6. Its subgroup of H is equal to 0 to 3. The left cosets are order of H is equal to 0, comma 3 and 1 is equal to 1, comma 4. This example illustrates how cosets can be formed in practical scenarios. Cosets in symmetric groups. Symmetric groups are groups consisting of all permutations of a finite set. Cosets in symmetric groups can be used to understand the structure of permutation groups. They demonstrate how cosets can help analyze more complex algebraic structures. Cosets and normal subgroups. A normal subgroup is one where left and right cosets coincide. This means GH is equal to HG for all G in G. Normal subgroups are essential for forming a quotient groups. Quotient groups. A quotient group is formed from a group and normal subgroup. The elements of the quotient group are the cosets of the normal subgroup. Understanding quotient groups is vital for advanced studies in abstract algebra. Applications of cosets. Cosets are used in various applications, including cryptography and coding theory, helping classifying groups and understanding their structure. In computational group theory, cosets play a role in algorithms for group operations. Distinguish between left and right cosets. While left and right cosets can differ, they share many properties. In abelian group, left and right cosets are always equal. This distinguish between becomes significant in the study of non-abelian groups. Conclusion on cosets. Cosets are the fundamental concept in group theory with wide applications. They provide a means to explore and understand the structure of groups and subgroups. Mastery of cosets is essential for advanced studies in abstract algebra.